All right, so definite integrals. We have talked about already indefinite integrals, right? So indefinite integrals, that's where we see something with just the integral symbol, and we want to integrate, like, for example, cosine of x with respect to x. By the integral, by the way, what is the integral of cosine of x? What is the integral of cosine? Sine of x plus c. I know some of you said that first, but other people said negative sine of x, so I wasn't sure how to answer that. So, yeah, positive sine of x plus c, okay, is the integral of cosine of x, right? We can't forget these things because we're still going to be using them. I know you're right. We have only been doing shapes in recent memory. Okay. So now we're going to kind of bring together this idea of indefinite integrals and integration with the idea of area under the curve, and it all kind of comes together under the idea of a definite integral. Okay, so let me kind of define a definite integral. So for f defined on a closed interval AB. Okay, we denote the, and then in quotes, the definite integral of f over a comma b, right, as, so here's just how we write a definite integral, okay, and it's basically an indefinite integral, right, familiar things, our function, you know, the variable with which we are integrating, okay, so we're integrating with respect to dx here, right, because f of x, we're integrating with respect to x, but the one addition, since we're integrating over an interval, we add numbers here to our indefinite integral, and now it becomes definite. Indefinite is you're just integrating over the entire like real numbers, I guess, kind of thing. Definite integral, we are integrating over a defined, okay, interval, in this case, a to b. Okay. This, a, is known as the lower limit of integration. Please make sure all jelly beans get picked up off the floor, too, if they make it on there. And then don't feed me that one later on when you say, Mr. Wood, you want a jelly bean? This one tastes like floor.
That might be one of the flavors, actually.
Yeah, it could be. All right. And, of course, then B, we would know it to be as the upper limit of integration. Okay. One thing I want to mention here, B does not have to be a greater number than A. B does not have to be a greater number than A. So while the majority of the definite integrals that we do, A will be smaller than B, there will be definite integrals that we do when B is actually smaller than A. And we'll talk about what that means when we get there. Okay, we'll talk about what that means when we get there. Okay, yes?
So the words lower and upper don't pertain to the actual values of A and B?
Yes, they're lower and upper, but not in the sense of like numeric value, yeah. Exactly. Okay?
But does the first number in the interval always go on the bottom? And the second number in the interval always goes on the top?
Where you start, yes, is your lower limit integration, and then where you want to integrate to is your upper limit of integration then.
So it could go backwards.
Correct.
Oh boy.
Yes, because you could talk about like a velocity function over time, and if you want to find your change in position from time t equals 4 back to time t equals 2, so you can kind of like integrate backwards and figure out like an earlier position in time from that. Anyway, okay, one thing I want to mention here, this is very important, okay? A definite integral yields a value, okay, or number. Okay, so a definite integral equals a number. It will equal a number, a value, okay, a quantity. Indefinite integrals, when we answer an indefinite integral, we find an indefinite integral, we don't find a number or a value, right? I mean, if you look up here, we just did I showed you an indefinite integral. The indefinite integral of cosine x dx, did not equal a number or value, it equals another function, sine of x plus c. So an indefinite integral, okay, it will yield a family of functions. Okay, and the reason why I say family of functions rather than just a function is because of this plus c. Since that plus c, kind of can change depending on, what information we're given here, we say that this is then considered a family of functions. Sine of x is like, it's the family, and then the plus c is like the individual members. Whatever that plus c value is, that would be like an individual member. So it's like a family of answers there. Okay, so a definite integral yields a value always. So as soon as you put limits of integration in here, a lower limit, upper limit, you should end up, your answer should be a value. No limits, your answer should be a function. Okay, that's the key. That's one key thing to remember there. Okay, just keep that straight. Okay. So now, here's where we're going to kind of put together the integral and the area. So if f is continuous and non-negative, remember all the things we've been dealing with so far, our functions, our curves have been above that x-axis. We've been kind of avoiding talking about, what happens when we have a negative, when our function is below the x-axis. And we're still kind of avoiding that now. F is continuous, our function is continuous, and non-negative, so it's above the x-axis. And it's non-negative on the closed interval. Okay, AB. So if f is continuous and non-negative on the closed interval AB, then the area bounded, the area of the region, then the area of the region, question? A closed interval, you'll notice here, look at your interval. What do you notice about this interval? The brackets, right? So we're including the endpoints. So what do you think an open interval would be? Doesn't include the endpoints, exactly right. Yep, that's the difference. Okay, so then the area of the region bounded by the graph of f the x-axis and the vertical lines x equals a and x equals b is given by, and then I'll put colon here, area equals the integral from a to b of f of x dx. All right, so here we're now putting together that idea of area between a curve, the x-axis, and two vertical lines, right? So stuff we've been talking about. Let's see here if I've got a handy picture. Right, so back to something like this. Here we had a curve, all right, and we, between x sub 1, x sub 6 here, we're trying to find the area underneath that curve. Of course, it's curvy, though, so we weren't able to get the exact value, so instead we had to use trapezoids to estimate it. Well, now we're being told, okay, if you want to find, if you have a function that's continuous and non-negative on a closed interval, then the area of the region bounded by the graph, the x-axis, and those vertical lines A and B is simply the definite integral. That's it. It's just the definite integral. Okay, these are the same thing. All right, they're the same idea. All right, questions on any of that?
Is there just like another way of finding it?
Yes. But this is how to find the area precisely. Before, right, we were approximating. This is the precise way to find it. So as long as we can integrate whatever this function is, we can now find the area underneath whatever that curve is, precisely.
Now if we get a bunch of, like number 53, we couldn't integrate 53 because it's just a bunch of points. We have to have
Correct.
the original function.
Right, so, and yeah, for example, like 53, you just have to like estimate it because you only have points, right. So yeah, so like tables, for example, if we're given a table and we want to find like, we want to find the area underneath the curve, we still have to estimate it, right? But given an actual function now, we can actually find that area underneath the curve, okay? Now, let me kind of go one step further here and really show you what's going on. Notice, remember, what did we do when we were finding the area underneath those curves? We took in our very most basic sense, we took rectangles, right? We took the width of those rectangles and multiplied them by the height of those rectangles. Well, in our curve, let me see if I've got a picture of that handy. Okay. What did we use to find the heights of those rectangles? The function, right? I got pictures there. Oh, of course I picked up the blank one. Okay. But yes, we used the function itself to determine the height. And then we multiplied the height from the function times the little width of those rectangles, right? And the width of those rectangles was some distance x. Well, isn't that exactly what we're doing right here? We're taking the height of those rectangles and we're multiplying by a little width x. Okay, dx is representing like a tiny width of the rectangles, and then f of x is representing the height of those individual rectangles as we kind of go along our interval here, these x values from a to b. All right, so essentially we're going to add up an infinite number of these little rectangles that are infinitesimally thin, and we're going to create an actual an actual value for the area underneath that curve. So that's what's happening here. We're adding up an infinite number of rectangles that are infinitesimally thin, okay, and that allows us to then create this area. So let's actually see it in practice here, okay. So let's, for these first examples, we're going to start out kind of staying in our familiar kind of territory of geometry. So let's sketch the region corresponding to each definite integral and I think I've gone off the page here. I'm going to zoom out. Skosh. There we go. Okay. Sketch the region corresponding to each definite integral and evaluate each integral using a geometric formula.
It wasn't personal. It's whoever stood up
yes.
I'm sorry, Mr. Wood, our is too bright.
Okay.
Well, now it's popping.
That's right.
Thanks, Ryan.
Okay, so that's our directions here. We're going to sketch the region. That's our directions for this example. We're going to sketch the region corresponding to each definite integral and evaluate each integral using a geometric formula. All right, so we're not quite there to like doing the actual definite integrals and stuff like that, but we're going to at least use geometry to help us evaluate this. All right, so let's start with our first example here. We're going to integrate from 1 to 3, 4 with respect to x. Why do we start at the bottom and go up? Because again, it's like from the lower limit to the upper limit. So from 1 to 3 of 4 with respect to x. That's 1. All right. So again, we're not really sure how to evaluate definite integrals right now. All right, we haven't learned how to do that yet. All right, you two in the back, you already know how to do it, so that's fine. But you know, Trinity James, they got it. But we're going to do this using geometry instead, okay? Because that's what we know. We know that this is equivalent to the area of whatever geometric shape we create here. Well, let's sketch this real quick. We know what's the graph of 4. f of x equals 4. What's that?
Added in.
It's a horizontal line through 4, right? So let's just kind of, all right. We'll just sketch that line right there through 4. All right. And we're integrating from 1 to 3. That means our left boundary is at x equals 1. And our right boundary is x equals 3. The vertical line, x equals 3. Okay? Because again, what did we say? That a definite integral is equivalent to finding the area of the region bounded by the graph of f, that's the line f of x equals 4 here, the x-axis, that's the x-axis right there, and the vertical lines x equals a and x equals b. So if we look right here, here's x equals 1, there's x equals 3, and so what type of shape have we created here? A rectangle, that's right. So we're trying to find the area of this region. So that definite integral is really just asking us to find the area of that region. And so what will that be? 8. Yeah, it's 2, the width, times 4, the height, so 8. Say it again? That's right, the 1, the 3, and the 4, just add them all up. That's the answer. Yep, there you go. You figured it out. That's going to be everyone else from here on. This calculus is easy. No, yeah, I gotcha. That is funny. That is funny that it worked out that way. That's coincidence. All right, let's try another one. Let's try another one here. All right, so again, this one we're going to again use area to evaluate this definite integral because we're not quite ready yet to. What's that? Yeah, right, exactly. It's okay. This time the method fails. Just this time.
It would be really funny if it didn't fail.
Right. The Tyler postulate. The Tyler theorem, actually. We'd have to prove it. Or I guess we would just assume it to be true, so it would be a postulate. Okay. That's right. All right, so let's graph this. Say again? So a theorem is something that is proved to be true. And I didn't know this until I just started teaching geometry recently. A theorem is something that's proved to be true. So you prove a theorem using like postulates, definitions, things like that. A postulate is like a ground rule that isn't proved to be true. We just kind of accept it to be true. With the idea being that if it wasn't true, it would really mess things up if it wasn't true. You understand what I'm saying? So you start with these ground rules. So for example, and this is I think I've talked to you guys about this before, like Euclid developed geometry, all of his geometry with like 5 postulates. One of those postulates, though, the parallel postulate, which says that if you have a line and a point not on that line, right, there exists exactly one line that is parallel to the given line and that goes through that point, right? He says there's only one line. But it turns out there are other ways to develop geometry so that that postulate is not true, and so there are other geometries now because that postulate that we accepted to just be true is actually not always true. It doesn't have to be true, if that makes sense. So postulates are ground rules in math.
There's like different schools of thought.
But you don't. But postulates. So the idea is that we're accepting it to be true, but then sometimes we can develop other maths when we say they're not true. So it's interesting. Anyway.
Like, just I guess get more on how would that not be true?
So there are, for example, you can create, like, for example, geometry on a sphere. If you define a line, so like geometry on a sphere, you think like the Earth, right? If you think of like the equator, that would be called a great circle because it's a circle whose center is the center of the sphere, Earth, right? Or like the prime meridian, right? That like goes around the Earth that way too, but its center is the center of the Earth, like the circle of that center. So like if you call those lines, there's no way for, and like that's in the spherical geometry for whatever reason, great circles are called lines, defined as lines. There's no way to make there are no parallel lines in spherical geometry. You can't, because if circles are centered at the center of the Earth, all the circles will always intersect each other. So there's no parallel lines. And then there's something called hyperbolic geometry, which is also non-Euclidean, and then you can have an infinite number of lines parallel to a given line. An infinite number. And that's like apparently that. And again, you might be like, well, why is this made up? It's not actually. There is actually application to it in like space apparently, like how like the universe is laid out. hyperbolic geometry is potentially a real thing. So it's actually like useful. So pretty crazy.
I don't
it is
like
pretty
that.
crazy. Right, I know, right? Yeah.
Don't face dummies.
Well, it's like also so like once you change that one rule, everything changes. So for example, in spherical geometry, you can have triangles, for example, but triangles can add up to be more than 180 degrees inside. And in hyperbolic geometry, triangles can have sums of less than 180 degrees. So just that one thing changes, and like all the rules go out the window, and you have like a whole new system. It's pretty interesting.
So in school, we
So I can show you a sphere one real easy. A sphere triangle.
No, I want to see this.
Just real quick. Just real quick. Sorry, I know you guys. Some of you guys are like, "Come on, Mr. Wood, seriously."
No,
But I
it's not
like geometry.
serious.
Okay. All right. So let's again just think about the Earth, right? Okay. Think about the equator of the Earth, right? Okay. So that's like a great circle. And so let's create a triangle here. So what I can do is, if we have like the pole here. All right. If I drop, a line along the Earth down there, that creates what kind of angle right here?
Right angle.
Yeah, right angle, right? Because it's coming straight down and it hits the equator right there. Now, if I go out at a right angle from the North Pole here, all right, I'm going to drop down, and eventually that will also hit the equator
A right angle.
at a right angle.
Yeah, well, it's not a triangle.
So, no, well, okay, it's not a triangle in the sense that
It's not
in Euclidean
Euclidean.
geometry,
It doesn't look like
but in
this.
sphere geometry, it is a triangle.
Well,
Right? 3 sides, 3 angles, it's a triangle. So, but it adds up to 270 degrees, not 180 degrees.
I don't like it when math is broken.
Yeah, right, yeah, back to geometry. So anyway, I think it's just fascinating stuff. I learned that there's an entire class I took in college called Euclidean and non-Euclidean geometry. And obviously that is non-Euclidean geometry.
School we learn Euclidean.
Euclidean geometry, that's right. It's neat, yeah.
So somebody who does geometry for a living called a geometrist?
Geometer.
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 So they put the geometry.
Yeah, a geometer.
Mr. Bing is a mathematician. So he teaches
Yes.
class.
I did not what?
Like, I'm a nerd.
Oh.
And I was like, nerd.
Yeah, thanks. Anywho, all right, back on track here. Let's sketch this area. So what is this going to be, what is this shape going to be?
Maybe a curve.
Now granted, it's y, but I'm just going to do it with respect to x because, I'm just going to graph it here because we can just change it to x and stuff like that. It's going to be a semicircle, that's what it's going to be, okay? And it'll be a semicircle with radius 2. If I graph this here instead of using y's, using x's though, okay, so if we graph this, oh, I guess you can zoom 4 there.
Hey, look at that.
Okay, it's a semicircle. All right, and we're graphing from -2 to 2, so you can very clearly see here that we're going to have the entirety of that semicircle for our region. Okay, I was doing really good there, and then I just blew it. Okay, on the other side. Anywho, there you go. So again, seeing this for what it is, half of a circle, how can we find the area of this?
Well, first you're going to plot your lines.
So, okay, our vertical line. So again, so here's our vertical line at x equals -2. Here's our vertical line at x equals 2. And then the x-axis. So the region, this is important too, being able to identify the correct region. Okay? What is the region here that is bounded by all 4 of these things? -2, 2, the curve, and the x-axis. It's this semicircle right here. It's this. Okay, that's the region we want. So it's half a circle. So what is half of a circle?
1/2 pi.
1/2, yeah, pi times the radius squared. What's the radius of this circle? 2.
Yeah, 6.2.
So you get 2 pi, or approximately, 6.283. All right. So that's the idea. All right, so there's that. There's some basic definite integrals that we can evaluate using geometry. Now, let's finally broach the topic of negative area. Okay, what happens when the curve is below the x-axis?
Okay, is the application for this would be like economics?
There's a lot of applications. Again,
Or negative
any,
area?
I see what you're saying. I see what you're saying. You can think of like rates too and stuff like that. Sometimes you have positive rates and negative rates, and those will accumulate and then give you like a net change. So like sometimes you're increasing, sometimes you're decreasing, and then if you integrate over that, you'll get like a net change, which will give you the the end result. Kind of like, well, you went up here some, you went down here some, but at the final result, you ended this position, kind of thing. So economics, certainly yes, because the market fluctuates up and down. But then you can say the net change is that we ended up at this many points at the end of the day, kind of thing, something like that.
That could be acceleration too.
Yeah, absolutely. You can accumulate acceleration to figure out what your net change in velocity was as well. Because sometimes you accelerate up, sometimes you accelerate, you accelerate, decelerate, then you can get your net change. That's right. Okay, so here's what happens. Here's kind of the answer to this. So when we think about our definite integral, back to like the original idea here, all right, and I was telling you it's basically like adding up those rectangles again, where we had the height of the rectangles times the width of those rectangles. All right. In a definite integral, the value of it, well, let's see here. If our function value here is determining the height of those rectangles, if we're below the x-axis, what will that height be given as? What value, positive or negative? If it's below the x-axis, it's going to be negative. The widths of those rectangles, well, those will still be positive, right? We're still measuring from like left to right there, and so those will still be positive. So we're doing a negative times a positive, and so what will end up happening here? We'll get a negative value. So, considering the width, which again we know that to be basically like the dx, okay, remains positive, and the height value, okay, the height value, which is determined by f of x, okay, is now negative because we're below the x-axis. The value of the definite integral is going to be negative, which is kind of like what we've been wanting to say, I would think, right? Intuitively, we want to think, okay, if our graph is below the x-axis, then it would make sense that the value of that definite integral should be negative, because it's an area underneath the x-axis. Okay, so that's the idea with that. All right, so we'll look at some examples of that here. All right, so as an example, we're going to find the definite integrals over the given intervals. All right, don't get those words interval and integral mixed up. That's right. All right, so let's do the first one here. Integral from 1 to 4 of x minus 4 with respect to x. All right, we can sketch this to help ourselves out. All right, so let's sketch this here. So the graph of x minus 4 is just going to be a line. Okay, what's the slope of our line going to be? It's 1, right? And what is the y-intercept of our line? Negative 4, right? Yep, it's in slope-intercept form, so we can just graph this thing here. So I'm going to go down 1, 2, 3, 4. 1, 2, 3, 4. Okay. So there's our x-axis, there's our y-axis. Just get a nice sketch here. Am I going too fast for anybody? We're all good? Okay. So let's graph our curve first. So y-intercept is negative 4. And then we're going to go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, okay? And we kind of connect the dots there to make our line. All right. So our region is this entire little triangle right here, right? No, it is not. But you might say, but Ms. Whitmire, look, it makes it a little pretty triangle right there. And you're right, it does make a nice little pretty triangle. But what is our interval? 1 to 4. If we do this triangle, what interval is that? 0 to 4 as our boundaries there, okay? We want to go from 1 to 4. Here is 1, so we got to drop down a little vertical line, and then here's 4. We're going to drop down that one. Okay. So again, we have a lot of regions going on here. I see a little like trapezoid-looking thing right here. I see a triangle right here. I see some other shapes, okay? What region is the region that is bounded by our curve, the x-axis, and those vertical lines? It's this little triangle right in here. It is that triangle. That is correct. Okay. What is the area of this region? Well, how do we find the area of a triangle? Yeah, 1/2 times the base. What's the base of this triangle? 3. What is the height of this triangle?
4.
Negative.
1. Which one is it? What is the height of this triangle? 3. So 1/2 times 3 times 3 is 4.5. Negative 4.5. And technically we should make that like a -3 then, because we're measuring down here. So yes, the value of, so let me be very careful about this, right? Area is never negative. We're using the area to get the value of this space, okay? But then to give it, because it's underneath the x-axis then, the definite integral's value will be a negative 4.5. Okay, so be very careful about that to distinguish that, because it's very easy to get these kind of mixed up. Area and the definite integral are essentially the same thing, except for when we are underneath the x-axis. That is when area will still be positive, because area is always positive, right? But the value of the definite integral will be negative because it's underneath the x-axis. So we use the area to get the value, but then we make it negative because it's underneath the x-axis there. Okay, question?
So, how would you word a question in which that would be positive? And like if it says find the area of
Yeah.
the given interval?
Yeah, potentially, yes. And I'll highlight it when we get to that. Something like that. Yes, because you're right. It is kind of like, oh, which one are we looking for here? So I'll try to highlight that when we get to it, because right now I'm having trouble coming up with it off the top of my head. But yes, it'll be like, what is the area of the region? It'll be maybe later on when we do like volumes of solids of revolution. It'll maybe become a thing. So anyway, all right, let's try another one here. Integral from 0 to 6 of the absolute value of x minus 4 minus 2 with respect to x. Okay? All right, now some of you guys, when you see absolute value, right, you freeze up. Right? Because absolute value is uncomfortable for us. It's weird. It doesn't behave in normal ways, and so it's, not necessarily enjoyable. But we actually can do this with little difficulty. All right. If you guys recall, right, way back at the beginning of this class, we talked about function transformations. Okay? So what is the parent function of this?
Absolute value of x.
Yeah, just absolute value of x. But this version of absolute value of x is being transformed. How's it being transformed?
It's being shifted left to.
Okay, not left 4.
Right.
Right 4. Remember, the number with the x is opposite. Yeah, so it's right 4 down 2. And so we're going to take our traditional absolute value of x. Okay, we're going to take our traditional absolute value of x, and instead of having it start at 0, 0, it's going to shift 1, 2, 3, 4 to the left, and down 1, 2. So here's where the vertex of the absolute value of x is going to be. So there's where our pointy part is. Okay. What's the slope of absolute value of x? 1, yeah, it's the number in front. It's a 1. So from this point to the right, we're going to go up 1, right 1. So we go to there, and then up 1, right 1 again, and we get to the 6. And then what about to the left? The slope is really a negative 1, but again, we go up 1, left 1, up 1, left 1. Okay, and that kind of creates our slope there. And so we can create our region. All right, I can keep going to up 1, left 1, so on and so forth. Okay, so it's going to look something like that and that. Okay. All right, I see a bunch of regions here. So again, it's a matter of, we graph the function. We also have to consider the 0 to 6 part, though, too. So we have a kind of a vertical boundary line here at 0, and a 1, 2, 3, 4, 5, 6, a vertical boundary line at 6, too. Yes. So in this case, Connor correctly identified here, we have both positive and negative areas, right? We have this piece, and again, it's between the curve and the x-axis, so this piece is above the x-axis, but then the curve, since it goes below the x-axis, we then have this region right here as well that we are concerned with. All right? So how should we go about trying to solve this to get the end, to get our final answer here? How should we? What should we do? Ideas, yeah, Connor?
Should we find like the area or of the?
Yes, exactly right. We're going to find the area of each individual piece, combine them together. Exactly right. So you guys go ahead and do that. We all did, yeah. Did you finish it? So base and height always have to be perpendicular to one another. So actually, they would be perpendicular, wouldn't they? But you don't know this is a diagonal distance here, so what is that? But this yeah, first triangle is, I don't know, 2 times 2. 2. Second one is, we have to be careful. 75, I think it's 6. No.
2 times 2.
Good.
Is that only 2?
Yeah, this one's like that now. Two of that now. That's inflation. $9.99.
How much?
$9.99.
No, I know. Are you having trouble though?
I'll get back with Gaten. That's my
You got it okay there, Keelan?
Musker, plunger, and push one. That's the keyboard.
Yeah, maybe it's not
Musker,
working. I'll try that out, yep.
Musker, plunger.
So, when you have your areas here and your area is beneath the x-axis, you still find the value like you normally would, but then you make it negative because it's below the x-axis.
Use some nice plunger. Corky. We're using corky plunger.
Right process there, just don't forget it. And that negative is that's the easiest thing to miss because you just like, okay, it's in the area and you think, okay, I'm done. But no, you got to make it negative because it's below the x-axis.
They
kind of screamed my quadrant forward.
All right, what are you struggling with here?
I mean, either plunges or it doesn't. This one does.
How do you actually integrate it, right?
It's a crappy job that somebody's gonna do it, and it's plunges
We're
for
gonna
a
get
fine
there.
job.
Like right now, I want you guys to have an understanding of it.
By far the worst plunges I've ever owned.
There will be
I have had
situations
court
where
cases
the
passed, they change the degree of urban they use it, and it's constantly getting stuck and then inverted.
But again,
Never again.
that might still be
Whatsoever.
easy for you, but, yeah, we're introducing our make it sound this way first, and then we're gonna.
Better plunger than I thought it would be.
30. Do the integration. Plug in the
$3
plunges.
plunges. I know I plunges was so cheap.
All right. What we get?
I got the zero. I got me zero.
-2. Now, there will be cases where the areas will cancel out and make it 0, but in this case, the area of the bigger triangle it's more negative here, so then they cancel out. Okay. Which you can kind of see again these arguments for like like before. Now you're seeing how we can find the more negative areas over the more positive areas and stuff. How we were talking about before with increasing and decreasing and things. So there's that. All right. Let me talk about some other things here real quick, some other properties. So any questions on this actually first before I move on? All right. So two special definite integrals.
Oh. No.
Okay. This is almost like a property of a definite integral. Okay, special integral 1. If f is defined, okay, at x equals a, then, okay, so f is defined at x equals a, then the integral from a to a of f of x dx is equal to, what do you think?
0.
Okay, I hear 0. Any other ideas before I
Oh man, I would be.
give the big reveal here? So again, everyone really think about this here. We're integrating from a to a. So our left and our right kind of like boundaries are the same thing. What would it make sense as the value here?
0.
It's 0. It is 0. There's no value. There's no space between those things, so it's 0. There's no area that you can create when you go from a to a, so it's just equal to 0. All right, and then the second one, if f is integrable, obviously that means able to be integrated on AB.
Is that closed?
Yes, closed interval AB, sorry. Then, the integral of a to b of f of x dx, all right, is equal to negative integral b to a of f of x. All right, so integrating from a to b of f of x is the same thing as the opposite of the integral from b to a. So integrating left to right with the same interval is and then integrating from right to left, they'll just be opposite values from one another. Okay, so integrating from 1 to 4 here, we got we got negative 4.5. Integrating from 4 back to 1 would yield what answer? Positive 4.5. So integrating from right to left, even though the region is underneath the axis, because we're going right to left now, it's like double negatives. They cancel each other out and become positive 4.5. Here, integrating from 6 back to 0 would yield what as our final answer? From 6 back to 0 would yield what? Not negative 2, positive 2, the opposite. Okay, this area would now be considered like a positive value. This would be considered negative, and so they would just flip-flop the signs and become a positive 2. Okay, it's pretty crazy. All right, a couple other little things here I want to mention. Another property: if a function f is continuous on a closed interval AB, then f is integrable. That is, able to be integrated. I just made it up, so it's real. No, I'm kidding. It's in the math book. All right. If a function f is continuous on AB, then f is integrable on that same closed interval AB. Okay. So that's another little important piece. Continuity implies integrability.
So are all the properties the same as integral properties then? Most of them?
What do you mean by that?
Well, we know that if function is continuous on a closed interval for derivative, then it's differentiable on the open interval. So are they all the same?
Differentiability implies continuity, but continuity does not necessarily imply differentiability.
Oh yeah.
Right? So be careful with that. But yeah,
But
I think
continuity does imply integrability.
continuity does imply integrability.
Yeah, because it's going one step back.
Exactly. So it's like, imagine this. If you're talking about f and then its integral, you're really talking about f is like its derivative. So that means if f is continuous, that means the integral of f is differentiable, and so their differentiability is still implying continuity. It's still kind of the same relationship there. All right, last little thing here, and this is called the additive interval property. Additive interval property. Okay, so if f is integrable on the closed intervals determined by A, B, and C, so we have an interval from like A to B, an interval from B to C, right? Okay, so that's what I mean by that, like an interval from A to B, an interval from B to C. Then, okay, the following is true. The integral from A to B of f of x dx is equal to the integral from A to C of f of x dx plus the integral from C to B of f of x dx. Okay? Look at what's happening here. We're taking the integral from A to C, we're adding of a function, plus the integral from C to B. So basically we're kind of chaining these two things together. From A to C plus C to B, it then joins together, becomes just A to B. Right? The upper limit of the first one is combined together with the lower limit of the second one, and so we are putting them all together. Notice here, we are not told that C has to be between A and B, and in fact it does not have to be between A and B. C can be outside from being between those two things, and this still will hold true, okay? This will always hold true. So C does not have to be between A and B. All right, I'll give you a quick example here, and this is our last, this is it. Okay, so for example, given the integral from -1 to 1 of f of x is equal to 3, so we don't know what the function is, no idea, but we're told that the value of that definite integral is 3. And we're also told that the integral from 0 to 1 of f of x dx is 5. We want to find the integral from -1 to 0 of f of x dx. Close. Yes. All right, so let's take a look here. We just talked about combining together intervals to make one big interval. Which of these are we going to be combining together to make which of the big one? Right? Which one's the big interval here?
The leftmost one.
The leftmost one, -1 to 1, right? That's the widest interval we have here, -1 to 1. It is made up of taking the -1 to 0 together with the 0 to 1, right? -1 to 0 plus the interval from 0 to 1 yields the interval -1 to 1. Does that make sense now, Tyler? Well, we're trying to find this one, yes, but understand it's like basically saying it's going to be this one plus this one. So it's going to be some blank plus 5 has to equal 3. And so yes, negative 2. So that means this thing has to equal negative 2. These two together, because of their intervals, negative 1 to 0 combined with 0 to 1 yields negative 1 to 1. Because they're all talking about the same function, these two together have to add together to make 3. Well, 5 plus negative 2 makes 3. So that means this value has to be negative 2. Must be negative 2. Must be. Okay, that's the idea behind it. That's all I have to say about that. Okay. Yes, donkey is indeed.